So I have to be like, no, it's working, I promise. So, all right. Good morning. Here we go. We were dividing polynomial functions last day, and well, we started just talking about polynomial long division in general. So I feel like, no, our test isn't for a while. It's not until the 30th. So that's not what I wanted to mention. I think we're okay. Oops. Quick review. We started polynomial long division. Where we have a polynomial over a polynomial, which is also called a rational function, right? And so later today, we're going to graph rational functions, which sounds really scary. And in fact, it's going to look really scary, but it's not that bad. We'll develop kind of step-by-step procedures. So polynomial long division, if we have some p of x over q of x, and I will highlight here that this is called a rational function. Because here we have a polynomial divided by some other polynomial. Okay. So we said, okay, we can do that work, and we'll do 2 more examples today where we kind of really nail it down. And then, so I'm not going to do that now, but I do want to highlight that we can write our result. We can write our result in 2 ways. I'll even put in brackets equivalent ways, because they do the same thing, and we rearranged the equation last day to show that, yeah, they are the same. So I'll say 2 equivalent ways. We can either write p of x over q of x equals, oh no, it escapes me. Oh, sorry. We're going to use p of x over q of x in the next section. Here we're using d of x. Sorry about that, guys. Because it's the divisor, so okay, fine. It's the one that we're dividing by. Okay, so, but don't be confused later when we use q of x, because here we use q of x for the quotient. And then plus r of x over d of x. D of x is, of course, the same d of x that we have here. And then r of x is the remainder. Hopefully ringing sort of a bell here, where we found the quotient and the remainder, right? Or you can write p of x equals q of x, or yeah, it doesn't matter, q of x d of x. So just multiplying this d of x over to the right hand side, but that means we have to multiply it by both terms, right? So then plus r of x, because it's going to cancel with that d of x in the denominator. Now, as long as we're able to find q of x and r of x, right? So as long as we're able to find the quotient and the remainder, we can construct the answer in any way we want, right? We just kind of plug it in. So as long as we are able to find the quotient q of x and the remainder, r of x, oops, that doesn't look like an r of x, we can construct the answer in either way. We can construct the answer either way. So that's not the hard part, but I do want to highlight that they're the same. And then your WebAssign questions will ask, set it up in this way or set it up in that way. But the work is going to be to find the quotient and the remainder. We also talked about, we had a chance to talk about the remainder theorem. And so, and then I want to start with introducing the factor theorem, because then we have all the information from this section, and then we'll go do our examples. So a little bit kind of backwards, but we also talked about the remainder theorem. The remainder theorem, which we had on our handout here. So some things to highlight here is that it's only true for if you're dividing by something like x minus c. So we're going to see some examples. The examples that we're going to do, I don't think 11. Yeah, so 11 and 14 that we're about to do stray from the x, so stray from dividing by x minus c. So it's not going to apply to those problems. But last day, the first example that we did was the only one actually that that had that format of x minus c. So it's kind of a special case, I guess. And so if you have p of x over x minus c, and then you find q of x and specifically r of x, right? So the remainder, then the remainder is the polynomial evaluated at the c, right? And so that's kind of weird, but also kind of cool. Okay, so here, what this says is that if p of x over x minus c equals q of x plus r of x over x minus c, or the other version works too. Right, the key is this guy here. Then r of x equals p of c, right? The polynomial evaluated at c, which is from here. Pretty weird, but that's the remainder theorem. It works every time. And for some reason, it's a learning outcome for this course, and you've learned it. I don't know. So of course, for me, it's more important that you're comfortable with the long division. And then when you have the remainder, I might ask you, okay, so what is p of c, right? So if you are saying you have this polynomial divided by x minus 3, right? And then I might ask you, what's the polynomial evaluated at 3? Making sure that, so one thing to note, if dividing by x plus 3, for example, right? Then c equals -3, right? So you want to be really careful because it's x minus c, right? Since x minus -3 equals x plus 3. So that's something to keep in mind. Okay. And we looked at that last day, so kind of new today, I want to get into the factor theorem. The factor theorem works back into the remainder theorem, so that's why I'm skipping to it. Okay, the factor theorem. The factor theorem is this. Let's see here. Where is it? We've already used the factor theorem, even though we didn't call it that. C is a zero, meaning it's an X-intercept, right? So if something is a zero, that's just another term for an X-intercept. Intercept, yeah. So C is a zero, meaning C would be an X-intercept, right? Of P, if and only if X minus C, so you're dividing by X minus C, is a factor of P of X. Now let's just link it back to the remainder theorem. So what does that mean? Well, it would mean that our remainder would be zero, right? But then if you're dividing by something that sets this thing equal to zero, right, X minus 4, let's do an example actually. We'll do an example after I write that down. So here, if we find that R of X equals 0, we can conclude C is a root, right, or a 0 of P. Right, and again, it only works if you're dividing by X minus C. Okay, so let's do an example here. Okay. Let's do 54, because I don't want to go crazy with the 1/2, and I also don't want to check 2 roots. So I am being a little bit lazy, but this whole numbers are about as, and single whole numbers are about as far as I would expect you to go. So it's fine. All right. So what we're saying is, okay, so we're asked to use the factor theorem to show that X minus C is a factor of P of X for the given value of C. Okay, so really what we're saying is that, okay, we've got P of X is X to the 3 plus 2X squared minus 3X minus 10. Okay, and D of X in our case is going to be X minus C, but C is, we're forcing it to be 2. Right? If you glance ahead to 56, and when you have to let C be -3, that's exactly what we just talked about, right? Then you would have X plus 3 as your divisor, right? Okay. So what we have to do here is we need to do some long division, okay? One thing that I want to point out, because it's going to come up later today, is we need to make sure, and maybe green is better. We need to make sure that starting from the highest power of X, we have powers of X for every decreasing value, right? So starting at X to the power of 3, we need to have an X to the power of 2 representative, we need to have an X representative, and then we typically have a constant representative, right? And so we need to show all powers of X starting from the highest power, if that kind of makes sense. So we need to make sure all powers of x, starting from the highest power, starting from the highest power, are listed in P of x. For example, so here, just as a side note, if P of x was, if I asked you to just do x to the power of 3 minus 10, okay, we would need to write P of x equals x to the power of 3, and then here I'm adding plus 0x squared plus 0x, and then I can go back to minus 10. So you have to fill it in, and you just put coefficients of 0, because this is equivalent, right? 0 times whatever goes to 0, so it goes away, but we need little placeholders for each of these x's. Okay, it's going to be really important because it can really mess stuff up when you're doing your division. Okay, so now we're ready to divide this thing. X minus 2 is going into x to the 3 plus 2x squared minus 3x minus 10. Oops. Okay. All right, remember how we did it? We're going to take the first term, right, the leading term of the big guy, the p, and then divide it by x in this case, right? And so, and then the result goes up above the x to the 3. Okay, so I'm not going to do all the different links and stuff. Most of this division I can just do in my head, right? So x to the power of 3 divided by x, I know is x squared, right? So I have x squared up here. No, kicking it up a notch from last day where we wrote everything on the side, and that's totally fine. But I just want you to see how, I guess, how little work you can get away with. Okay, so then x squared, you now have to multiply down to x minus 2, and then you put the result below the x to the 3, and then we subtract them. So x squared times x is x to the 3. And then x squared times negative 2 puts me at negative 2x squared. And then it's important that I subtract both of those terms, right? Key is, well, what has to happen is these guys have to go away, the x to the 3 minus x to the 3, because that's the whole reason we're doing this. We're kind of chipping away at each of these terms until we have none left. So x to the 3 minus x to the 3 puts me at 0. And then just be careful bringing in this negative, right? So 2x squared plus 2x squared puts me at 4x squared. Okay. And then I want to bring down whatever is left. So minus 3x minus 10. If you prefer to keep them up here, that's fine, but then your eye just has to kind of jump around like in this kind of S shape, or not really an S shape, but so that's why I bring them down. But I mean, you don't have to, but it make it cleaner to look at. Okay, 4x squared divided by x puts me at 4x, right? So here I'm at plus 4x. And notice that I stack them on top of the term that I was just dividing into, right? And then now I can go 4x times x minus 2 is 4x squared minus 8x. And then that has to get subtracted. Okay. Again, the goal here is to now be done with the x squared term so that it should zero out, right? And so here 4x squared minus 4x squared goes to 0. Negative 3x plus 8x puts me at plus 5x, hopefully. I don't know. Negative 3 plus 8 does. I had a long night, so who knows? And then bring that minus 10 down. So minus 10. So now we're so close. This is our last time that we're going to be able to divide, right? Because I need one x, at least one x, to be able to divide. And then the rest will be a remainder. So 5x divided by x, positive 5x divided by x puts me at plus 5. Now when I multiply that down, so 5 times x minus 2 puts me at 5x minus 10. Looks familiar, right? So now I have 5x minus 10 minus 5x minus 10 looks pretty good to me. So I have 0 plus 0. So what I've found here is that r of x equals 0. Okay. So here's where I'm going to outline the remainder theorem as well as the factor theorem. So by the remainder theorem, remember the remainder theorem says that, okay, if I'm dividing by x minus 2, right, then the remainder theorem says that the remainder, whatever the remainder is the polynomial evaluated at 2. Okay. So by the remainder theorem, we find r of x equals 0. So p of 2 equals 0. Okay. Which leads us to the factor theorem of, okay, well, if I'm plugging 2 into this polynomial and I end up at 0, well, that's where it crosses the x-axis, right? So that's where y is 0. So, so then that makes it a factor. And so by the factor theorem, c equals 2 is a factor of p of x, since r of x equals 0, which leads us to p of 2 equals 0, right? And that's what it means to be a factor. And you can try it. We're not going to do that, but you could try, right, putting in 2 to the power of 3 plus 2 times 2 squared minus 3 times 2 minus 10, and should end up at 0. Okay. So that's the remainder and factor theorems. Now let's go ahead and just practice some more long division. I think I said we were going to do 11 and 14. So I want to start with 11. Remember, you could use synthetic division, but it only works for x minus c if you're dividing by x minus c. So that's why I always just use long division. So even if it says synthetic division, you can just use long division, right? Sometimes those WebAssign questions say use synthetic division, but just go for it with long division. It'll still work. Definitely. All right. So 11, we want to find And maybe I'll just, because I have the question here, maybe I'll just set it up right away, right, with our little divisor. And then we'll be off to the races. 2x minus 3. I'll leave a little bit of space above, right, because I need room for my quotient. Did I mention last time? I didn't, right? But whatever we find up here is our q of x, which is our quotient. That's from last time. All right, so we want to do 2x minus 3 going into 2x to the 3 minus 3x squared minus 2x. So first thing I want you to do is just check for to make sure that all your powers of x are there, right? So starting at x to the power of 3, I have an x to the power of 2, I have an x, and then let's just jot down a constant of 0, just so we have that placeholder for the constants. It would be fine if we didn't, but it might be nice to see it there. Okay, so a little bit more division here. 2x to the 3 divided by 2x puts me at what? X squared, right? So I'm going to write x squared up top. Then I take x squared and now I bring it back down. So x squared times 2x minus 3 puts me at 2x to the 3. That's good. Minus 3x squared. And then I want to subtract that. First term is going away, which is good. Negative 3x squared plus 3x squared. Okay, so now just notice that here you have 0x squared if you want to emphasize it. You could just put 0, but sometimes it's nice to see the 0x squared. So what happens, so 0 divided by anything, especially 2x, right, is going to just give you 0. So that's nice because then we can jump ahead, right? And so what we get here is we get plus 0x technically, right? If you 0x squared divided by 2x, you could just write 0, but it's nice to have the decreasing powers of x here. And then 0 times that, right? Nothing's really happening. So you could jump ahead to this minus 2x. I'm going to bring it down because I forgot to do that. Minus 2x plus 1. Oh, plus 1, that changes things. Plus 0. I morphed it in the process. But just to follow the same procedure, let's just do 0x times 2x to the 3, right? And just show that nothing happens here, right? So you can skip the 0x, but then just make sure that when you go for this term, you write it up here, right? So you kind of have 0 in here just to visualize it, but it doesn't actually do anything. You can skip. Yeah. So then, cool. 0x times 2x, well, that's 0x squared if we're pretending. 0x times minus 3 is 0 minus 0x. Subtracting, right? Just following the rules of the road here. Puts me at 0, and then negative 2 plus 0 is negative 2x plus 0, right? I'll say here, we could, could skip this step. Okay. So you don't need to have that step. You could go straight to dividing into negative 2x plus 0. So now if I have negative 2x divided by 2x, Negative 2x divided by 2x is -1. And then -1 times 2x minus 3 is -2x plus 3. Just make sure here. Yeah, looks good. And then that's being subtracted. So of course this first term goes to 0 like we need it to, and then we have 0 minus 3. So what we've found here is that therefore q of x, I'm going to try to keep it on the same page here. In fact, I'm going to need one more line. So I'm just going to bump this up one line. There. So here, your q of x is whatever's on top. This 0x isn't really here, right? So q of x is x squared minus 1. And r of x is -3, right? We have a remainder of -3. Okay. Good. I'm not going to construct the answer because we have all the components, right? We have p of x, we have d of x, we have q of x, we have r of x. You can put those in whatever way you want. So we're not going to do that. I want to do another example, kind of a big mumbo jumbo here. So I think 14, right? Okay. So first thing you're going to do is you're going to check your p of x and make sure that you have powers of x for each term, right? So here our highest power of x is 5. So then I have 5, 4, 2. So I need to bump it out, right? I need to fill it in with a 3, and then I don't have just an x, so I need to fill it in with 2 terms. So we need to write p of x equals 27x to the 5 minus 9x to the 4, and then I'll use a different color here, plus 0x to the 3 plus 3x squared, right? And then I need an x too, plus 0x, and then finally minus 3, right? So I'm just filling in all those terms that aren't there, but we need those placeholders for those x's. It's a big one. We can do it though, right? Notice here we're dividing by a pretty large polynomial too, right? So 3x squared minus 3x plus 1. Here, I don't think, well, it's not something you have to worry about, but I actually don't think we need to have all the terms listed properly here. I don't think so. I think we can just go for it. So what I'm kind of mumbling about is, do I need to do this one, 3x squared minus 3x plus 1? I have each of the terms, but if I didn't, would I have to do the same thing as I did here? I don't think so. But I honestly, I might have to look into it. I don't know. So if you find one like that, let me know. Let me know if you have to or not. Okay, so let's set this up. 3x squared minus 3x plus 1 is going into that big thing that we just set up, 27x to the 5 minus 9x to the 4 plus 0x to the 3 plus 3x squared plus 0x minus 3. Okay. Now, I'm not gonna try to be a hero here. I will do this math kind of over on some scrap paper, but I'm actually out of space here. So, so it'll be kind of, well, in my head, but just remember 27x to the 5 divided by 3x squared. So working with those exponents, I know I end up with an x to the 3, but 27 divided by 3 is 9. So then 9x to the 3, right? 5 minus 2. You can always just double check that what you did made sense, because when you multiply it back down here, it should subtract out, right? So it should subtract the first term. So 9x to the 3 times 3x squared, it puts me back at 27x to the 5. 9x to the 3 times negative 3x. So 9 times 3 is, oh, sorry, again, 27, of course, minus 27x to the 4. And then 9x to the 3 times 1. And that's why we need this x to the 3 here, because otherwise you would be subtracting x to the 3 from x to the 2, and that's where things go terribly wrong. So we have 9x to the 3 times 1, so plus 9x to the 3. So even though it's a little bit longer, we still just put our answer down there and then subtract it. So first things first, this goes to 0, and then I have negative 9 plus 27, putting me at plus 18x to the 4. And then I have 0 minus 9x to the 3, so minus 9x to the 3. And then I can bring these guys down here, plus 3x squared plus 0x minus 3. Okay, on to the next one. So now 18x to the 4 divided by 3x squared. So 18 divided by, oops, did 4 for some reason, 3 is 6. So plus 6x, 4 minus 2 is 2, right? But notice our powers are going to start at x to the 3 and then decrease by 1 until we're finished, right? So 6x squared times 3x squared should put you at 18x to the 4th. And then 6x squared times negative 3. So 6 times 3 is, why do I keep doing that? Keep doing the same math over and over again. 6 times negative 3, negative 18x to the 3. And x squared times x is x to the 3. And then we have 6x squared times plus 1, so plus 6x squared. Make sure you subtract all of these. 0 for the first term, that's good. And then I have negative 9 plus 18 is 9x to the 3. And then I have 3x squared minus 6x squared, putting me at minus 3x squared. And then I'll bring down these other two terms, plus 0x minus 3. We just keep going, right? We keep going until my x's, the remaining x's, right, can't be divided by x squared, right? The highest power in the divisor. You'll also know when you can't divide anymore, just when you'll see it when you get there. So 9x to the 3 divided by 3x squared, I can still do that, right? And so 9 divided by 3 is 3. So I have plus 3x now. Makes sense. I have x to the 3, x to the 2, and then now x. So okay, checks out. So now if I do 3x times 3x squared minus 3x plus 1, I get 9x to the 3 minus 9x squared plus 3x. And then I'm going to subtract that. So I get 0, that's good. And then minus 3 plus 9, so negative 3 plus 9, just checking here, 6x squared. 0 minus 3x puts me at minus 3x. And then I'm going to bring that minus 3 down. There's a couple of reasons I know that this is my last step, right? Because I'm down to just one power of x, so x. So I have room for a constant here if I find one. But also I see that 6x squared is the last term that's going to be divisible by x squared, right? So a couple of reasons why this is the last step. So looks good. Okay, so 6x squared divided by 3x squared puts me at 2. Right? Positive, positive, plus 2. So now 2 times 3x squared minus 3x plus 1 puts me at, I'm running out of space here. 2 times 3x squared is 6x squared. 2 times negative 3x is minus 6x. 2 times 1 plus 2. But then I'm subtracting that still. Right? Don't forget to do that. This guy goes away. Negative 3x plus 6x. So yeah, plus 3x. Negative 3 minus 2 is minus 5. Let me just check here. For my notes here, I have 3x plus 5, but I think that's wrong. Looks like it's minus 5. Feeling confident, so it's probably a typo. Okay, because it was me writing it out, so grain of salt, right? Okay, so good. Now there's no more division that I can do here, right? I would need to divide by 3x squared, but I only have 3x. So then I would be getting into the negative powers of x's, which I don't want to do, right? So we stop here. So what we found is that this is our q of x, and maybe I should use a different color here. So our quotient is this big thing here. This is our quotient, and here, this is our remainder. And so I'll just summarize it here. We have found that, let me just see if I can copy it here. It's 3x plus 2. So we've found that q of x is 9x to the 3 plus 6x squared plus 3x plus 2, and r of x is 3x minus 5. And then, so now you can take those bits and you can construct the answer in either of those two ways that it asks for. I think for these questions, they wanted you to write p of x. Oops, sorry, it's catching up. I think they wanted to write p of x equals d of x. So that's the one that we were dividing by. And then times q of x, which is the quotient that we just found, plus r of x. Now, I do want to say that you're just going to leave them as they are. You're not going to expand them out or anything. So, so just plug them in and leave them be. Right? Expanding them could get really, really big and bad. Okay. So, in fact, let's just have. We want to write it like this in this case, because I guess no harm in writing it out once. So p of x is, in this case, it was 27x to the 5 minus 9x to the 4 plus 3x squared minus 3 is the divisor, which was 3x squared minus 3x plus 1 times q of x, which is 9x to the 3 plus 6x squared plus 3x plus 2, and then plus the remainder, which is 3x minus 5. So here, this here is p of x, this here is d of x, q of x, and r of x. And you do not need to expand this out. Do not expand. Just plug in your values. Right? So you would just leave it like this. So what can we use this for? Well, if I really had to factor out a 3x squared minus 3x plus 1, that's what I've done here, right? I've written it as a factor of 3x squared minus 3x plus 1. So we can force kind of factor out bigger terms if that's what we're finding. But for us, we're just going to practice doing our log division, and then if we're dividing by x minus c, then we'll just be able to use the factor and the remainder theorem. But that's about it. Okay, so we can take a quick break before we start section 3.6, which is on graphing rational functions. So how about we do a little break until 8:55. How about that? Grab some water, caffeinate. Even without a response, I'm just going to do it. Okay, so 3.6. So we don't do a lot of sections in chapter 3. We've just kind of cherry picked what we want. 3.6 is graphing rational functions. What I want you to remember throughout this whole section is that, of course, I want you to check your work in Desmos, right? So although all this seems kind of like a lot, I still want you to just, when you've done something, right? So if you've decided that you've found the X-intercept, for example, then graph it in Desmos just to make sure that you found the right X-intercept, right? So you can always check your work for this section. So that's really nice, because otherwise it can be quite a bit, right? So rational functions. So now a rational function is a polynomial over a polynomial is a polynomial over a polynomial. And like I defaulted to earlier, usually we'll use p of x over q of x. So we use p and q typically to denote polynomials. P is obvious polynomial, and then I don't know why we use q, but so it's no longer the quotient, it's its own thing. So context, of course, matters here, p of x, q of x. So not to be confused with the quotient, not to be confused with the quotient, oops. these two things will never overlap. So the context it'll be clear which is P of X and which is, or if the Q of X is being divided into P of X or if it's the quotient. So, so it will be obvious, but I just wanted to point out that don't let it confuse you. So now what we're going to be building up towards is we want to be able to graph big nasties, or at least sketch a graph of something kind of big and nasty like this, right? And so we're building up towards sketching graphs of a polynomial over a polynomial. Notice here that our highest power of X seems to be, besides this X to the power of 3 in number 57, I don't see any powers of X that are higher than 2, which is nice, right? Because just looking ahead, we will have to factor these things. And so if the power of X is 2 or lower, well, is 2, then we can use the quadratic formula, right? Like we've been doing. So, but notice here, X to the power of 3, but then I also have minus 3x squared. So I can factor out an X and then I'll have a quadratic again, right? So all of these, we're kind of maxing out at quadratics. So, and we know how to deal with those, right? So that's what we're building towards. We want to develop just a procedure to be able to graph something like this. And so let's see here. How about I just grab this last one just to talk about. Okay, so in this section, we develop the procedure for sketching the graph. We're not drawing it perfectly, but we are sketching it, getting a good idea of how this thing behaves. And that's going to be really useful later on, right? Especially in calculus when you need to know the behavior of functions, right? So if we can tackle these big ones, then that's great. So we'll develop the procedure for sketching the graphs of functions like, oops, like this. And maybe I'll cut that question number here. So here, I'm going to call this guy P of X and this guy Q of X, right? So when I refer to them, instead of saying the numerator, which is P of X, and the denominator, which is Q of X, I'm just going to talk about them as P of X and Q of X, right? So we'll use these as shorthand. Use this shorthand. Okay. Just so we can talk about them kind of quicker. So first thing we need to discuss is horizontal and vertical asymptotes. You might remember asymptotes. Asymptotes are, you know, if a graph is approaching a point, but it's not actually getting there, so maybe they're increasing together, but never actually approaching that value. So let's see here, where is that little guy here? So first thing we're going to talk about is asymptotes. So we can have vertical asymptotes and horizontal asymptotes. And I think I've mentioned it before, or at least I definitely mention it in my calculus class where we have to talk about vertical and horizontal all the time. So if you have a hard time with remembering which one is which, well, the horizon goes like this, right? So that's horizontal, and then vertical is the other one. So if you have a line x equals a, so some point x equals a, then you can have a horizontal asymptote. It can be going towards positive infinity, or it can head to negative infinity. And to make matters worse, we can be approaching a from the right, or we can be approaching a from the left, right? And so if we zoom in here, it didn't really, it's all blurry, okay? I think I've got it in another thingy. Mark this up so I can grab it, yeah. I'll add this in here so we can talk about it. Okay, so notice that if we have, so x approaches a and then a power of a negative, it means as we're approaching a from the left. Okay, so approaches a from the left. So in this case, right here, I'm approaching this a, this line at a from the left. Okay, so we might have different behaviors, right? We might have something like maybe at a from the right on this graph, maybe it's going down towards negative infinity, right? So we have different behaviors depending on which side of a we're coming from, right? And so these are our different options. So it can go down to negative infinity or up to positive infinity. It's gonna, how we decide which way it's going, it's gonna follow the procedure that we used in 1.8 with inequalities. Okay, so we'll have done it sort of before. Okay, and then same thing here. If you've got an a plus, it means you're approaching a from the right. Okay, and then we can talk about, okay, so for vertical asymptotes, we're talking about the behavior of y as we approach some value of x. For horizontal asymptotes, right, so what can happen is we might approach some horizontal asymptote. There are scenarios where we don't have any horizontal asymptotes, and that's totally fine. But again, we're going to talk about how do we decide if we have horizontal asymptotes and what are they? Okay, so we need to kind of have a good handle on these asymptotes. All right, so how do we decide if we have horizontal asymptotes or not? Let's see here. Well, and vertical asymptotes. So here, blow this up. Okay. I have a generic polynomial over a generic polynomial, right? This is a polynomial, so on top, the p of x is a polynomial degree n, confusing because they use n and m, and in the denominator, so q of x is a polynomial degree m, okay? And each of them have a leading coefficient. So here, I'm going to say p of x is degree m with a leading coefficient, oops. A subscript n, right? So it just whatever the leading coefficient is. And then q of x, the denominator, q of x is degree m with a coefficient b subscript m, with coefficient b subscript m. So, oops. the first part here says that the vertical asymptotes are at the lines of x equals a, where a is a 0 of the denominator. Now, how we have been approaching this is when I ask you to find the domain, right, you're looking for values where you're not dividing by 0, right? And so now, kind of on the flip side, those values where you would be dividing by 0, they're making vertical asymptotes, right? Because we can't happen, our function can't happen there, and there might be some weird behavior shooting off to infinity or negative infinity, right? And so just to kind of write around this, the first point says that in P of x over Q of x, the values that make Q of x equal to 0, right? They're not in the domain. So the values that make Q of x equal to 0 are the points where we have vertical asymptotes. Are the points where we have vertical asymptotes. Okay. That's great. So kind of the reverse of finding the domain, right? Or I think it's easier if you just try to find the domain. Where does this thing equal 0? And then at those points, you have vertical asymptotes. Okay. Often the easiest way to find where those things equal 0 or what values make it 0 is by factoring, right? And if we're only dealing with quadratics at most, then we know how to factor a quadratic and we know how to find the zeros of the quadratic. So we know how to find vertical asymptotes, right? It's just, we haven't taken it that extra step before. So now, in the second point, okay, now we're going to be comparing the degree of P to the degree of M, right? So if N is less than M, so if the degree in the numerator is higher than the degree in the denominator, or sorry, is less than, wow, that would be confusing. Don't listen to me. No, if the degree in the numerator is less than the degree in the denominator, then you're going to have a horizontal asymptote at y equals 0. So that's nice. That's on the x-axis, right? So that means we have a horizontal asymptote on the x-axis. So as x goes to positive and negative infinity, we kind of plateau off around the x-axis. So here, to determine if we have horizontal asymptotes, we compare, we compare the degrees of, and this is where I'm going to start using that shorthand, of P of x, which is degree n, and Q of x, which is degree m. Okay. So the first option is n is less than m, then y equals 0 is a, and I'm going to say just shorthand HA, horizontal asymptote. And I'll clarify that here. Horizontal asymptote. Usually we write HA and VA for vertical asymptotes. Save us some writing. Okay. Okay, so you're going to compare these degrees, and if the degree in the numerator is less than the degree in the denominator, you're going to have a horizontal asymptote at y equals 0. If that's not the case, then you move on, right? Oops, not to C, probably to B. If n is equal to m, so if they have the same degree, then you're going to have a horizontal asymptote at the coefficients over each other. So a subscript n over b subscript m. Now notice, and that's why I highlighted what the leading coefficients were, right? Because then you're looking at the coefficients as a fraction, those leading coefficients. So if n is equal to m, then y equals an over bm is a horizontal asymptote. Right. And I'll just clarify that these are the leading coefficients. And then finally, if the degree of the numerator is larger than the degree in the denominator, then there is no horizontal asymptote, and that is totally fine. Notice that we've covered all the different scenarios, right? And so sometimes we don't have a horizontal asymptote, and that's okay. So, and then finally, if n is larger than m, then there is no horizontal asymptote. Great. Okay. So two different ways that we find. So we find the vertical asymptotes by figuring out where is the denominator equal to 0. And then we find our horizontal asymptotes by looking at the degrees in the numerator and the denominator. And then potentially looking at the leading coefficients. So some other things that we might be interested in to sketch our graph are definitely the intercepts, right? And then we'll also look at the behavior around the vertical asymptotes, right? To sketch the graph, we will also need to find the X and Y intercepts. So the intercepts, just as a refresher, the X-intercepts are when Y is 0. So the X-intercept, potentially, can have more than one X-intercept. The X-intercepts we've talked about before, it's where it crosses the X-axis, right? So the X-intercept is where Y equals 0. So what do we have to do? Well, that's only going to happen, right? Or where R of X equals 0. In fact, R of X equals P of X over Q of X equals 0. What we need to remember is that this whole fraction or quotient, we'll call it later, which is confusing. So I'll call it a fraction. This whole thing can only equal 0. The only way for it to become 0 is if P of X equals 0. Okay, so R of X can only be 0 if P of X equals 0. Now, the easiest way to find where P of X equals 0 is to factor this thing and find the roots, right? And so the easiest way to find where P of X, and notice, right, again, I'm going to focus on just quadratics, right? So, and we know how to factor and deal with quadratics, find the roots of quadratics. We've worked a lot with quadratics, right? So, so we're sticking to those. But the easiest way to find where P of X equals 0 is to factor, right? Is to factor P of X, okay, to find the roots. To find the roots, which we can also call the zeros. Zero is. Okay. So if you're keeping track, right? Now we've decided that I'm going to factor Q of X to find vertical asymptotes or potential vertical asymptotes, right? But then I'm also going to factor P of X. So as a first step, what we're going to say is just start by factoring both the numerator and the denominator, and then it'll make things easier as we go along, right? So first stop, factor both of these, right? Factor the numerator, factor the denominator, and then you'll be able to jump in to find all the information that you need. But that is outlined in the step-by-step procedure, so I'm going to hold off on writing that down for just a little minute longer. The y-intercept, remember the y-intercept is where x equals 0. That's easier to find, right? So this is where x equals 0. So in R of x equals P of x over Q of x, let x equals 0. So then the y-intercept is R of 0. Oops, that doesn't look like, clean that up, which is P of 0 over Q of 0. All right, that's probably the easiest one to find is the y-intercept. Where does it cross the y-axis? So then you can just let x be 0. Right, so that's kind of the fun one that we saved for last. Okay, I think we're ready for the steps. So a lot of steps. What's nice for you guys is, right, typically if we were meeting in person, I would make you actually sketch a graph on a test. For you guys, you'll just be picking the appropriate graph, but you'll have to outline all the information, kind of step-by-step information. So you do need to know how to find the information, but you won't need to necessarily construct the graph because you can check all that with Desmos, right? So you can still check your graph with Desmos and pick the right one. So, okay, let's go through these steps, but these are the steps that we just outlined, but this is how we're going to be able to go through and solve all these problems. So like I said, first thing we're going to do is factor the numerator and the denominator, right? Because we find that, okay, to find the X-intercepts, I need to factor the numerator, and to find the vertical asymptotes, I need to factor the denominator. So I may as well just do it from the get-go. Then I'm going to find the X-intercepts by determining the zeros of the numerator, right? And so that's why it's nice that we've factored it already. Whoops, something happened here. And then we're going to find the y-intercept from the value of the function at x equals 0. So it actually goes through and tells you what to do. Now for the vertical asymptotes. So the vertical asymptotes, you're going to find them by finding the zeros of the denominator, right? And that's why we started by factoring the denominator, okay? And then we're going to use test values. So just like we did for inequalities, we're going to find test values to see if y is going to positive infinity or if it's going to negative infinity. And we're going to have to test the values on either side of that vertical asymptote, right? This is probably the hardest part of sketching these graphs. And then once that's done, then you're off to the races, right? So then the next step is to find the horizontal asymptote. You do that by just comparing the degrees of the numerator and the denominator. And then here it says, using the procedure described in the box. Of course, that's not true. Above. Right, we just talked about it. I gave it to you. And so for those horizontal asymptotes, right, you compare the n and the m. And then you're going to graph this thing, right, by constructing things like the X-intercepts, right? So plotting your X-intercepts, plotting your Y-intercept, graphing your vertical asymptotes, potentially laying down your horizontal asymptotes, and then we'll kind of be able to sketch a graph, right? We're not drawing a proper graph. We're just trying to sketch the behavior of this thing. So I want to do a problem, not from the notes because I want you to have those, but it's actually from the textbook. That's okay. It means you don't have to read this part of the textbook. So let us do an example. This is example 5 from page 301, which doesn't actually help you because you're probably in an online textbook from the textbook. And I think I might have an old edition. Anyways, you'll be able to find it. But this is just so we have a good example to follow with. Okay, there's a lot of stuff that we need to do here. Oh, nice. Does yours look like this? Cool. Yeah, I can't remember. I can never keep up with the additions. They keep changing the additions. Okay, then it's on page 301. And there are a couple of other things, like if we have, so we're assuming that there are no common factors in the numerator and the denominator. And if there's time, I'll talk about that, but I don't test you guys on it, so that's why I'm kind of, if there's time, we'll cover it. If there isn't, it's okay. What we're covering is plenty. Okay, so maybe I'll say this. I'll say page 301 of 7th edition. I don't know. Okay, so we've got r of x equals 2x squared plus 7x minus 4 divided by x squared plus x minus 2. Okay. So first thing we want to do is just kind of study this thing, right? Right away, I have some pretty good ideas of what is going on here, right? Especially because I have the same power. So that's the first thing I can do. It's not the first thing we will do, but it's nice to just familiarize yourself with this function. So step 1, we decided we would just straight away, we would just factor this thing, right? And so what's nice, if you look at some of those problems that I'm giving you, some of these, well, the first 2 don't even require factoring. There's no factoring really that can be done here, right? And then they make you use the quadratic formula a little bit, but then here we have it factored already. And then so some of these have already been factored for you, right? So maybe that's a nice place to start if you find one that's been factored for you, and then build up to one where it hasn't been factored for you. That might be nice. And so even though 53 is in the middle, I think it might be a nice place to start, right? Because it's all factored and laid out nicely. Okay, so first, step one, we want to, step one, factor P of X and Q of X. And I will just highlight here that P of X is this and Q of X is the denominator. All right, just kind of using that shorthand is fine. So I've got two quadratics. So I know how to factor those, right? Because we spent quite a bit of time doing that earlier. And I want to highlight my steps as I go along here. So P of X is 2x squared plus 7x minus 4. Now, remember, this is a quadratic. So we have x equals negative b plus minus the root of b squared minus 4ac over 2a. Hopefully I'm remembering that right, but feeling pretty good. So x is negative 7 plus minus the root of 7 squared minus 4 times 2 times negative 4 divided by 2 times 2. All right. This is going to give us, and remember, a quadratic, right? It can cross the x, or it will cross the x-axis twice if it crosses the x-axis. If we find that we're taking the square root of a negative number, all that means, because we can't do that, right? All that means is that it might be pointing up above the x-axis, right? Meaning it won't cross the x-axis, or it might be pointing down below the x-axis, right? And so so that's okay, that can happen, right? Then you can't factor it. In this case, it won't happen, but it can. So we have negative 7 plus minus the root of, and maybe I'll just do the math real quick here. I'm just going to do it on the side. 7 squared is 49, minus 4 times 2 times negative 4 puts me at 81, and then the square root of that is 9. Plus minus 9. I skipped showing some work there. That's okay. Factoring, as long as you're able to factor, you can just kind of rip through it if you want to. You can show as many steps as you want to, but this is kind of, we're trying to factor, so we're just trying to get there. So we have minus 7 plus 9 over 4, and minus 7 minus 9 over 4. And these are all our zeros, right? So the values of x that make this 0. So we have negative 7 plus 9 divided by 4 puts me at 1/2. And negative 7 minus 9 divided by 4 puts me at negative 4. Remember what we did when we wrote out the factors. So x equals 1/2 is the root, right? And so later on, we know that these are our x-intercepts, right? 1/2 and negative 4. But when we're trying to factor, right? To factor, we know we have to bring this 2 over to write 2x equals 1 and x equals negative 4. So now we can construct this this factor, so then P of X equals 2x squared, oops, plus 7x minus 4. We can also write it as 2x minus 1, right? Because when 2x equals 1, it has to go to 0, times x plus 4, because when x equals negative 4, that term has to go to 0, right? As long as one of these are 0, it goes to 0. You should always check, right? If you've factored something, because factoring can be hard, right? So always check your work. 2x times x is 2x squared. Okay, so far so good. And then 2x times 4 is 8x. And then minus x, okay, so that puts me at 7x. And then negative 1 times 4 is negative 4. So it checks out, right? And so you should always check to make sure that it equals, that what you're saying are actually equal. So now do the same for q of x. Right? So now factor q of x, which is what? X squared plus x minus 2. X squared plus x minus 2. Now well, actually, we don't need those brackets. You might be one of those crazy factoring whizzes who is able to look at this and say, okay, something that has to add to 1 and multiply to negative 2, I don't know. I've given up on that a long time ago. It doesn't make sense to me. It's really hard for me to see. So I just stick with the quadratic formula. It'll always work. It's a little bit longer, but there's no harm in it, right? And so here I get x is negative. Now I'm not even going to write down okay, fine. Negative b plus minus, sometimes I don't even write down the formula, I just plug stuff in. B squared minus 4ac over 2a. So x is going to be negative 1 plus minus the root of 1 squared minus 4 times 1 times negative 2 over 2 times 1. So x is negative 1 plus minus, and then I have 1 squared, which is 1, minus 4 times 1, oops, I did times 4, times negative 2. Putting me at 9, which is a nice square number. So I have plus minus 3 over 2. So x is going to be negative 1 plus 3 over 2 and negative 1 minus 3 over 2. So negative 1 plus 3 is 2 over 2, which is 1, and x is negative 1 minus 3 is negative 4 over 2, puts me at negative 2. You might have looked at that quadratic and said, my factors are 1 and negative 2, great. But like I said, I don't see it, so I just go through and do it. So it doesn't matter how you factor. But you have to factor. So then we've got q of x, which I'm just going to copy here so I'm not scrolling up and down so much. So we have q of x is x squared plus x minus 2, which we can rewrite as x minus 1, because when x equals 1, it has to go to 0, and then times x plus 2, because what we're saying is when x equals negative 2, this thing has to go to 0. So you always kind of do the opposite sign in your factoring. Let's just double check here. So x times x is x squared. X times 2 is 2x, but then minus x puts me at 1x. And then -1 times 2 puts me at -2. So it checks out as well. Dink. Great. So now what we can do is we can rewrite the original function. And so now we can rewrite. Now we can rewrite, and where's that original function here? Just gonna grab it. Okay. As, what was it, 2x minus 1 times plus 4. Over x minus 1 times x plus 2. So, okay, that's step 1. A lot of work happened there, right? But it was to help us with the next few steps. Okay, so step 2 is the intercepts. Find the intercepts, and I'll highlight it so that we can scroll around here. I'll start with the x-intercepts, right? The x-intercepts are a little bit harder because those are the values of x that make r of x equal to 0, right? And so here, the x-intercepts, and I'll kind of do a little yellow underline here because it's like a subgroup. The x-intercepts are where y equals r of x, in this case, equals 0, right? And so what we have to do is find where p of x, because this is what we just established, where p of x equals 0. From the work that we did with our factoring, right, we said, okay, this thing factors to 2x minus 1 times x plus 4, but we also said, well, that's because when x is equal to 1/2, right, then we have a 0, and when x is equal to -4, I also have a 0. So we actually have already found the x-intercepts, right? Here, x equals 1/2 and x equals -4 are the x-intercepts. And from earlier, or from factoring p of x, we know x equals 1/2 and x equals -4. Should probably write those in the opposite order, right? Often we'll read them as if they're on a number line, just kind of makes sense. In fact, let me switcheroo those. And x equals 1/2. That's better. Are the roots Therefore, the x-intercepts are at x equals -4 and x equals 1/2. And in an attempt to keep this all the intercept stuff on the same page, how about I move it up just 1? So then the y-intercept, and I'll underline it in yellow again, is where x equals 0. Depending on which version of r of x, so really what you want to do is you want to find r of 0. R of 0 is either the first one that we started with x equals 0, that's fine, or if you prefer, to use the factored one, you should end up at the same answer, so it doesn't actually matter. I like to, whenever I can, go back to the original and it doesn't change the answer. I like to use the original because that's the one that I can rely on. Here, I've meddled with things, right? I'm feeling confident because I checked my factoring, so it should work. But whenever I have the opportunity to go back, and this is just me personally, whenever I have the opportunity to go back and use the original function, I will. Right, and so, but you can use either of these. So let's see here. I'm gonna copy this. So R of 0, let's see here. Now I'm going to swap these all out. Easier to write it all out, I guess, but I didn't want to be scrolling back and forth trying to remember what all these values were. R of 0, 2 times 0 squared is 0, plus 7 times 0 is 0, so all I'm left with is -4 in the numerator, and then same thing in the denominator. All I have in the denominator is -2. -4 divided by -2 puts me at 2. So this is our Y-intercept. Therefore, there's a Y-intercept at Y equals 2. I'm trying to keep it all on the intercept page. So we already know quite a bit about this graph, right? I know where it's crossing the x-axis. I know where it's crossing the y-axis, right? And so now we need to just keep working on this a little bit. And let's see here. Step 3 is finding the vertical asymptotes. Let's see here. The vertical asymptotes. This is why we factored the denominator, right? So we factored the numerator to find the x-intercepts, and then we factored the denominator to find the vertical asymptotes. So vertical asymptotes happen when q of x equals 0, right? Because we can't divide by 0, so here we'll have these kind of jumps. So q of x equals 0, q of x we have already factored and we've worked it out. So I'm going to grab it here and copy, paste. So q of x equals this. And so here it's easy to see that when x equals 1 and when x equals -2, we have vertical asymptotes. So x equals 1 and x equals -2. We have vertical asymptotes at x equals -2. Again, I'm just going to try to list them from smallest to largest, and x equals 1. Okay. All right, so what I want you to try to do, because I know I'm out of time here-ish, got like another minute or two, but now the next step, so next day we will find the behavior around x equals -2 and x equals 1 using test points. So very similar to what we were doing before, right? At -2, and you want to just have enough space to do all these calculations. And so here at 1, because you're going to have these kind of fake vertical asymptotes, and then you want to pick test values that are close by, right? And then evaluate how does R of X behave. So now just remember, and I want to set you up so that you can try it over the weekend, and then have like something under your belt before we start it next week. So R of X is this whole factored thing. So this is when I use the factoring because, oh, sorry, it's lagging. But here, so I'm going to use R of X equals this. Copy. Paste, make it small. And then what you want to do is just pick a value just to the left of -2. So this is going to represent how does it behave as I approach -2 from the left. And then you're going to pick as you approach -2 from the right. And then you're going to do the same thing around 1, making sure you pick values, and you don't have to pick specific values if you don't want to. But what happens is on this, so as I approach -2 from the left, if I'm thinking about -2.1, for example, right, that's just slightly to the left of -2, 2 times -2.1, and then -1 gives me a negative value. -2.1 plus 4 gives me a positive value. -2.1 minus 1 gives me a negative value. And -2.1 plus 2 still gives me a slightly negative value. So overall, overall I have a negative times a positive, that's a negative over a positive. So overall I have this negative behavior. So what I can say is that, okay, looks like it's going to go like this. And just like that, I'm out of time, but we'll keep working on that next day. And this is the hardest part of graphing these things, and then we're gravy. All right. If you have any questions, let me know. Otherwise, have a great weekend, and see you on Tuesday.